Hi guys, in the last class we were discussing about the efficiency chart, which is by the National Renewable Energy Laboratory, which is the NREL, which comes under the Department of Energy USA. So the main objective of this session is that we'll be looking at what is the current status of research across the world, and we'll look at how far we have reached in the field of photovoltaics. So this data that is represented over here in the form of a chart represents almost all the technologies that are used for solar cell, for the fabrication of solar cells, and this is from around the world. So this is like a organization. They have various labs, as well as they have this efficiency certification kind of stuff, where anybody from any lab from the world can actually apply if they have efficiency which is better than what has been recorded till now, and if they can reproduce it in the lab, in the NREL lab, if they can fabricate and show the efficiency, which is the IV curve, from which you can see calculate what is the efficiency. So in their lab itself, if we can get an efficiency which is greater than what has been reported till now in the particular field, then your cell will be recorded, or you can put up your cell will be put up on this chart, showing that you have achieved a world record efficiency in that particular cell. So we had already discussed about the Shockley-Queisser limit, which is the 33%, but here we can see that the efficiencies are going about 33%. Here you can see that there is a 47.1% efficiency cell. So I think in the last class we discussed how this happens, or how we can achieve efficiencies greater than 33%. So these are cells with multiple junctions. So here you can see that there is something written as 6J, which means that there are 6 junctions. So these are also concentrated cells. Concentrated in the sense you are giving 143 sun. That is what is meant by 143x. So 143x means it is 143 times 1 sun. So 1 sun is approximately taken as 1 kilowatt per meter square. So this is the approximate power that reaches the Earth's surface. We have already seen what is solar constant, which is 1.367 kilowatt per meter square. So what we consider is that let's say roughly around 33% gets reflected back, and therefore we take this value as 1 kilowatt approximately, which is considered as 1 sun. So 143 times means the light is being concentrated using artificial concentrators. Basically these are lenses which can concentrate light onto the cell, and on the they look at the efficiencies on the cell. I mean, they calculate they use a light source which is having 143 times the this value of intensity, and then they the light source is concentrated to get this value, and then they shine it onto the cell, and from the cell they take the IV characteristics by changing the resistance across it, and they get the IV characteristics, and from there they calculate the efficiency, and it turns out that you can get it is reported that they have got efficiencies up to 47.1% with a 6 junction solar cell. So this was reported by NREL itself. So this was not from somewhere else. NREL itself has reported this cell, And there are, you can see that there are various organizations which have reported all these cells. So this cell has been reported very recently. If you look at the year, you can see that the year is somewhere near to 2020, which means that it was reported very recently. So that is the highest efficiency till now reported. So in the last class, I think we have already discussed what is a 6-junction solar cell, or how it can enhance the efficiency, or how we can enhance the efficiency using a multiple junction solar cells. Like we already saw that, let's say if you have various junctions, let's say the various junctions are basically, they are kept one on top of the other. So what happens is that one of the junctions, generally what we do is that we have the junction which has the highest energy gap. Let's say the energy gap is somewhere around 3 electron volts or 3.5 electron volts or whatever it is. So the highest energy gap cell is kept on the top so that it can absorb most of the high energy radiations. And what happens is that the rest of the radiations passes through the first junction and it gets absorbed at the second junction. So what happens is that effectively some of the light is absorbed in the first junction. Rest of the solar energy gets transmitted to the next junction, and let's say the next junction is having some energy gap of 2 or 1.5 electron volt. So if it is 3 electron volts, we can roughly have an idea. 1240 divided by 3 is somewhere around 400 nanometers. So somewhere around 400 nanometers and less will get absorbed over here in this first junction, and then the next junction is 1.5. If we take it as 1.5, you get that the value is somewhere around 800 nanometers. 1240 divided by 1.5 is somewhere around 800 nanometers, approximately 800 something. We leave out that a few nanometers because there is always some energy loss, because of which we leave out few nanometers. So only the energy that is somewhere in this range of 800 nanometers can only excite the semiconductor with this band gap. And finally we have the third semiconductor or the third junction. This is just an example to show how you can enhance the efficiency. So what we said was that with a single junction, the maximum efficiency is 33.7%, which is the Shockley user limit. But if you have multiple junctions will absorb at multiple points, and you get a much better efficiency. And you can theoretically you can go up to 89% or so. That is what is there in the literatures. But then practically that is not possible. That is only possible if you have like infinite number of junctions, but practically that is not possible. And if you look at the data that is there from across the world, you can see that people have only reached up to 47% at the max. And this is with respect to the solar spectrum, very specifically with respect to the solar spectrum, and therefore you can't compare it with any other spectrum. Let's say if you have another spectrum, a light source with a spectrum something like this. So for this light source, if you calculate the input power, and if you have a semiconductor which can absorb all the light from this portion, maybe this entire portion could be efficiently absorbed, and your output by input theoretically might be much higher than the Shockley user limit. because this limit applies only to the solar spectrum. So if we take a different spectrum, this limit may not be this limit cannot be applied, and you might end up with better efficiencies. But there is no point in calculating that, because I mean, to some extent, maybe if you are looking for solar cells that can be used in indoor applications, maybe that is possible. But if you are looking for solar cells for capturing the sunlight, then this is not valid. We don't have to consider this case at all. But if you are looking for indoor applications, like if you want to absorb some of the light that is there in the inside your rooms and inside your houses, then maybe you can look at what is the spectrum that is there with the general lighting, or the general the sources that you use at homes, maybe the LED lights and the CFLs or the fluorescent lamps that you use. So accordingly you can calculate. So here we can see that the light is concentrated, and you have 6 junctions where you got 47.1% efficiency, and below that it is somewhere around 46 or 44% efficiency, and it goes on like that. So this is the technology with 4 or more junctions and concentrated light, right? And then the next one you can see here is the 44% efficiency. So this is 3 junction concentrated. So you can see which is this this triangle with a circle inside is the 3 junction concentrated one. So it has achieved a maximum efficiency of 44% at 302x. So 302x means that is the number of times of the sunlight that is being used for getting this particular efficiencies. So 302 sun, that is the light source concentration, and at that much amount of light they've got this efficiency at that concentration of 40. They've got an efficiency of 44%. So here they have 3 junctions, here they have 6 junctions, they have used 6 junctions. Now if you look at without concentration, what is the highest efficiency? You can see with 6 junctions, NREL has again reported efficiency of 39.2%. so this cell is also fabricated by the NREL itself, or developed by the NREL itself, not by any other organizations. So they have put up this record of 39.2% efficiency without concentration, and this is also a 6 junction solar cell. And let's look at what are the other technologies that are there. So here you can see there is the 3 junction non-concentrated, which is just below, and that has got an efficiency of 37.9%, which is over here. So this was reported somewhere in the range of let's say, I think 2013, right? So this was reported somewhere in the range of 2013, and there is no progress after that. I mean, this was the highest efficiency that was reported. And you can see that 3 junction with no concentration, it has not progressed in the past let's say 7 years or so. So you can see that these efficiencies are the recent ones. So here you have the year axis, and then here you have the efficiencies. So if you look at the other technologies, this entire chart has been divided into 5 different categories. So these are the multi-junction cells. Then you have the single junction gallium arsenide cells, and then there is the crystalline silicon solar cells, and you have some thin film technologies, and some of the emerging photovoltaics. So if you look at the emerging technologies, so emerging photovoltaics, you can see that these technologies started very recently. The oldest of the emerging technologies was the dye sensitized solar cell, which started somewhere in 1991. But then most of the other technologies have started after 2000, or they have been initiated after 2000. And some of the technologies, if you look at this perovskites solar cells, you can find that these have started just in after 2010. These are very recent technologies, and we can hope that since it has not these technologies haven't been there in the research groups for long time, we are expecting that these technologies can even go higher in their efficiencies. Because let's say if you look at the CIGS or the silicon solar cells, which are solar cells that has been that are being researched upon from around, let's say around from 1975s. So that's like around probably 40-45 years. So that is the depth of research that we have from 1975 to 2020. So that is around 45 years. We have been researching for around 45 years on these solar cells, which are the silicon solar cells or the gallium arsenide, and the some of the thin film technologies, and also the multi-junction solar cells as well, some of them. So no, I think multi-junction solar cells have started somewhere over here. Yeah, but most of these solar cells have been researched from very long itself. So they have kind of they have almost reached their highest efficiencies. If you look at this graph, goes somewhat in this direction. So this is the basic analysis that we can look at this graph. So with 45 years of research, it has somewhere reached in the range of near to 30% efficiencies, and with multi-junction solar cells, you can see they might have gone even far beyond 30%, because they have multiple junctions. But with single junction, if you look at the efficiencies, they are close to the theoretical maximums. So these are kind of almost stabilized, or they are getting stabilized in these efficiency ranges. But then if you look at the I mean, these have been researched for such a long time, and we have already produced materials that can encapsulate these solar cells with very good efficiencies, which means that they can stay up to around 20-25 years, the silicon solar cells. And that is where we have reached with these silicon solar cells today. And definitely the other solar cells, the emerging technologies, they are not as stable as silicon. They are still being researched. So silicon is kind of stable, which means that it can give up to operational efficiency up to for 25 years or so. But then if you look at some of the other solar cells, the emerging technologies, these are not completely stable. These are still under research. So emerging PV is still not stable. The encapsulation materials are still being researched for these photovoltaics, as well as these are very much humidity sensitive. So if the encapsulation is not perfect, then this can easily degrade very fast. And yeah, so let's look at what is a single crystalline. So I hope you guys know what is a single crystal. So single crystal means all the crystals have the same orientation. So if the bulk of the material has a single orientation, we call it if every crystal is in a single orientation, then we call it as a single crystal solar cell. And then multicrystalline means the crystals are not oriented in the same direction, they have multiple directions of orientation. So basically the problem is that single crystal solar cells are the crystalline silicon solar cells. If you look at crystalline silicon solar cells, you will find that the efficiencies of crystalline silicon solar cells are somewhere around this is the efficiency 27.6%. so 27.6% with concentrator and 26.1% without concentration. 27.6% for crystalline silicon, or you can say single crystal. With single crystal solar cell, you can see that the efficiencies are 27 single. Okay, just a moment. Yeah. $27.6 is with concentration, right? Yeah, with concentration, and we have got efficiencies up to 26.1% without concentration. So this is where the current status of research across the world. And if you look at multi-junction solar cells, multicrystalline, you can see there's the square that is there. So if you look at the square, you can see the efficiencies are around 23. Let's look at it. So the efficiency is around 23.3%. Yeah, so multicrystalline silicon solar cell has an efficiency of 23.3%. so we'll just discuss why this there is this huge difference, because single crystal, the fabrication of single crystal solar cells or single crystals of silicon is a hectic task in comparison to multicrystalline silicon, because single crystal silicon, the fabrication process itself, we'll be looking at the fabrication process in later videos, but in comparison to multicrystalline silicon solar cells, where you don't have to bother about the orientation of the crystals, it is very tedious task to orient all the crystals in a single direction and get a single crystal solar cell. But the advantage is that the electronic properties are much better in a single crystal, because since the orientation of all the crystals are in one single direction, it is very easy for the electron to get transferred from one end to the other. And this is the major difference which is there between these two materials, or these two structures, and this has a huge impact on their efficiencies as well. You can visibly see it, that the efficiencies are way too far. One is having 23%, the other one is having around 26%. So but then if you look economically, which is better, people might go for multicrystalline silicon solar cells, because these are much more cheaper in comparison to single crystal, because the fabrication process is very costly in comparison to multicrystalline, and therefore people compromise on the efficiency and go with this silicon solar cells, multicrystalline silicon solar cells, so that they can be economically benefited as well. And now if we look at some of the other efficiencies, we can see that the emerging photovoltaics, like the dye sensitized solar cells, these has got dye sensitized solar cells have had a maximum efficiency of around 12.3%. so you can see it over here. So these are solar cells that are fabricated from sometimes from organic materials. The dyes are collected from the organic materials, or people even use inorganic dyes as well. So that depends upon the fabrication technique that you are going to use, or that depends upon what is available, what are the available resources. So what they generally do is that they collect a dye from you can make inorganic dyes, which means you are using some chemicals, and by using just few chemicals you can make some dyes, or you can extract dyes from fruits or some flowers or some natural organic materials that are seen around, and then you can extract these dyes, and then you can check what are the absorption coefficients of these dyes, and then what is the absorption that you can achieve with these dyes, and you can use them for solar cell application. These are very simple devices. And then you have these perovskite solar cells. I think we have already seen what is this perovskite solar cell and what is the chemical structure of these cells. Then you have perovskite silicon tandem. So this is like two different junctions. One, you have a perovskite cell, and then you have a silicon cell, which means that you have two junctions. It's similar to a two junction cell, where the perovskite cell will absorb some part of the spectrum, and the silicon will absorb some the lower range energies of the spectrum, of the solar spectrum. And then you have the organic tandem cells. Organic cells are also very similar in construction to the perovskite solar cells. You use organic materials or organic compounds as the absorption for absorption, and then these organic compounds can absorb the light and then convert it into electricity. So then you have the inorganic cells, quantum dot cells, and perovskite CIGS tandem cells. And these are some of the thin film technologies. Silicon is not a thin film solar cell. The average thickness might be in micrometers, a few micrometers, but then if you look at the silicon solar cells generally are in the range of probably 20 micrometers thickness. So in terms of solar cells, these are not thin films, but then for there are some of the thin film crystal structures for the amorphous silicon solar cells, or the thin film crystal structures are also there. Those are some of the emerging technologies that are used very recently. But then the normal single crystalline silicon solar cell or the multicrystalline silicon solar cell, we use a thickness of around 10 to few tens of micrometers, somewhere around 20 micrometer, as I remember, is the thickness of the general silicon solar cells. But then if you look at some of the emerging PVs, the absorber for perovskite is only around 300 nanometers. So the film thickness of the absorber is only 300 nanometers, which can absorb most of the light. So that are the improvements that are being made from silicon to some of the emerging technologies with very thin films. So in comparison with 20 micrometers, 300 nanometers is very small. So that's why we call them the thin film solar cells, or these don't come under this thin film category in this categorization, but these are thin film solar cells. These are in the range of nanometers, and or you can say nanoscale. So these are the solar cells that we have discussed from this chart. So broadly what we want to say is that some of the technologies have started very recently, and we are still looking for better efficiencies with the emerging technologies and better stabilization with the emerging technologies. But if you look at the technologies that are there from like probably 40 or 45 years, these technologies are almost stabilized with this period of research, and we have a considerably good output from these solar cells, considering the fact that the theoretical maximum efficiency that we can achieve is around the Shockley user limit, that is 33%. So in comparison to the theoretical limit, the technologies which have been researched for 45 years, we can say that they have almost reached a good value which is comparable with the theoretical value. Moving on, but the problem here is that these are the lab scale values, but when you move from a lab scale value to a module, so this is the module efficiencies. So if you look at the module efficiencies, we can see that the module efficiencies are not that great. So in comparison to what we have achieved using on a small cell, the module is considered as a very large area device. I mean, there are multiple cells, and they are manufactured as a module itself, so that they can be commercially sold. So when you go from lab scale to commercial scale, the problem is that these efficiencies further drop down. So that is another issue that we have. So if we look at the silicon multicrystalline solar cell, which is the first one that is mentioned here. So if you look at this, so we can find it out over here. So that is around the efficiency is 20.4. so this is the maximum efficiency that you are getting with on a module scale. But in the research with the cell, we saw that it is somewhere around 23%. So there is a drop in the efficiency when you go from lab scale to module scale. And if we look at some other solar cells also, you will see the same drop in the efficiency. And you can also look at the time frame from which we have been producing these modules, and we are using them for energy applications or for producing electricity from solar modules. So in the module scale, if you look at, you can see that there is a cell with 40% efficiency, which is a hybrid 4-junction concentrated module. So with 4 junctions, we have seen that the efficiencies were somewhere around 44 or 46%, 44 to 46%. But then when you look at the modules, that is for research lab scale efficiencies, but when we look at the modules, the efficiencies have dropped to 40 to 40%. So that is the change in the efficiency when we go from lab scale cell to a module. Now if you look at some of the emerging technologies, so it is reported that the perovskite solar cells have an efficiency of 17.9 on a module. But then if we look at what was the efficiency that that is maximum highest efficiency that has been reported, you can see that the highest efficiency reported is 25.2% for the perovskite solar cells. So here it is. So so that is the difference that you can see when we go from the lab scale cell to the module. So that was around 25.2%. It has come down to 17.9% since when you manufacture it on a module scale, definitely what happens is that the efficiency that you get for a single cell cannot be matched with that of the module. So that is a major problem in commercializing these cells. And so I think with that we can also look at what are the years from which these modules have been being produced, and what is the current status of this research, and all these things you can look up from this chart. That is the major advantage of this chart, that you don't have to go around all the places, or you don't have to go around looking at all the papers to find what is the highest efficiency that has been reported. All the certified efficiencies are there in this chart, and you can get the efficiencies of almost all the varieties of solar cells that are being fabricated around the world. You can see what is the highest efficiency that has been reported by the NREL, or that has been reported in NREL. Basically anybody around the world, from around the world, they can go and fabricate the device in the NREL lab, and if they can produce the same efficiencies, they get it will be put up on this chart. So this is a very easy way to find out what is the current research level, or you can say the data according to today is this is one of the most reliable source. So according to today, this is the status of research across the world in this photovoltaics. So I think with that we'll wind up this today's session, today's video, and then I hope you understood this, how you can use this chart to understand or to learn which are the technologies that are emerging and which are the technologies that are being stabilized, and what is the current status of research across the world. Thank you guys.